So Newton's divided differences are what we're going to look at in this video. In the last video on Lagrange interpolation, you saw one of the weaknesses of Lagrange interpolation is the fact that if we have an extra set of points that we want to use to look at a higher order Lagrange interpolation, we have to start from scratch. Newton's divided differences actually overcomes that issue by looking at, in fact, lower order polynomials and then add on as we have more and more data. So the objective of Newton's divided differences works something like this. So you have data points. Suppose these are our data points, x0, y0. So these are just in pairs, x0, y0, x1, y1 up to xn, yn. So the objective is if we have, so first we want to get a polynomial that interpolates this data up to n plus 1 data points, and then we'd go for the n plus 2 or n plus second data point, which is xn plus 1, yn plus 1. And when we get this point, we want to have a method where the previous polynomial, which would be this data would be represented by some Pn of x, okay, an nth order polynomial. And we want to say that, okay, now that we have this extra data point, we want to go to the n plus 1th, or go to Pn plus 1 without losing the work we did for the Pn. So kind of an add-on. One extra data point means we can add on something to the previous polynomial approximation under interpolation that we have to basically strengthen or make our polynomial approximation perhaps more accurate by including more data. So that's the idea and objective of Newton's divided differences. So the way it works is quite simple. We start with the simplest polynomial, which is a 0th order polynomial, the constant, and clearly we let that equal 0. Keep in mind that it satisfies the first point for sure. It interpolates only on one data point. So imagine that you started with just one data point. Now if you did start with one data point, you would be interpolating a 0th order polynomial, a constant, okay? And clearly that would be satisfied because here P0 of anything, in fact, is Y0. So P0 of X0 is equal to Y0, so it works. So let's say we move to, now this was just one data point. Let's say we move to 2 data points. So if we have 2 data points, then we would have P1 of x, and we would say that P1 of x is, the way we will design it, we'll say it's going to be P0 of x, the previous polynomial, which was from one data point only, plus some constant a1, let's call it, into x minus x0. Now why x minus x0, I'll explain in a second. The idea is that this second approximation, or second, includes the points x0 and x1. Now if we check this, P1 of x0, if you look at it, now you'll see why we have the x minus x0. Because P1 of x0 means that I put that in here, as I put it in here, the x0 minus x0 will make this whole thing disappear. So it'll all go to 0. So what I'll be left with is just P0 of x0. So I'm going to have P0 of x0, which we know is equal to y0. So in other words, this interpolation, P1 of x, satisfies, or at least interpolates the first point accurately. Now, it should, of course, interpolate the second point accurately as well. So that means that P1 of x1 should be equal to y1. Let's have a look at what happens, in fact, when we substitute this point in. So we have P0 of x1 plus a1 of x1 minus x0. Now remember, P0 of x1 is just going to be y0 because it's a constant function. So we end up with y0 plus a1 over x1 minus x0 should be equal to y1. Well, this gives us a very simple opportunity to figure out what a1 is. And a1 is in fact equal to y1 minus y0 over x1 sorry, over x1 minus x0. So we've got a formula for our a1. And this means that now we can in fact have a polynomial interpolation for our two data points. In the same way, let us go further and extend this idea to the second order polynomial. So now, instead of just the two data points, we'll have the third data point, which is going to be, which is in fact supposed to be x2 and y2. So let's have a look. So P2 of x, we propose, will of course use the previous polynomial, P1 of x, plus some additional pieces, or an additional piece, which will be the following. It will be a2 times. Now, what do we want to get rid of, remember? In the previous one, if you remember, I said we said x minus x0. Why? Because x0 was the previous point. Okay, so we wanted to get rid of, when we substitute the x0 in here, this disappeared. Now we have 2 points to get rid of. We have the x0 and we have x1 as well. So in order to do that, what we'll do is the following. We'll say x minus x0 into x minus x1, in fact. And what this will do is, when we go and check P2 of x0, that will mean P1 of x0, which is y0 like before, and plus when I put the x0 in here, it gives me nothing. So that's correct. In the same way, I will check P2 of x1, and P2 of x1 is going to be P1 of x1, and P1 of x1 we've already shown is equal to y1, as you can see here. As you can see here, P1 of x1 is equal to y1. This A1 definition makes that happen, makes that a reality. So P1 x1 is already equal to y1. And since x1 minus x1 is 0, so there's no contribution of this term. So therefore, that also seems to be fine. So that leaves our last bit, which is the situation where P2 of x2, in fact. Okay. So P2 of x2 works out to be equal to P1 of x2 plus a2 into x minus, or x2 minus x0 into x2 minus x1. So this means that, and this should be equal to y2. Okay. We rearrange the equation. Remember, P1 of x2 is not available right now. It is available. We can get it, but we'll have to substitute it in there and the previous expression for P1. But instead of doing that, let's just rewrite this for the time being as a2 is equal to y2 minus. Now we get this expression. The problem with this expression is there doesn't seem to be an emerging pattern. We need a pattern if we want to have an algorithm or a straightforward iterative formula. So in order to do that, let's expand on this P1 x2 for a moment. Let's look at what is P1 of x2. So P1 of x2, in fact, is going to be substituted into our previous formula here. This formula here, we'll have to take it all in. So in this one, so, and we're going to have to use this A1, in fact, and look at the entire thing together. Recall that P1 of x2, okay, will simply be calculated by using the previous formula. So it's going to be P0 of x2, which is just P0 of x2, which is just y0, because anything, so anything that is P0 will be y0. So it's y0, okay, plus a1, and a1, we know what a1 is. It's given as y1 minus y0 divided by excuse me, x1 minus x0. Now all of that is basically our a1, and that is all multiplied by, in fact, x1 minus x2 minus x0 in this case. So that's multiplied by x2 minus x0. Now what we're going to do is we're going to play a little trick here, and we're going to say that, well, wait, I can change this x2 minus x0 into something else. What I can do is, let me rub that out, because I can. And then what I'll do is I'll introduce an x1 and say an x1 plus and minus, and then bring back what I had before, which was the minus x0. So if you look at this little trick, what it does is basically we're going to group these numbers together, and what it does is the following. So, when we do this, the advantage of this is now as we multiply through, we get y1 minus y0 over x1 minus x0. All of this multiplied by x2 minus x1. But the second term, if you notice, the denominator cancels and leaves you with simply y1 minus y0. Now this y0 and this y0 cancels, and we're left with just y1 plus y1 minus y0 over, and I'll keep that separate actually, sorry, 1 second. Let's separate this out because these two seem to have some interesting connection to each other. Let's keep the x's together. So we end up with this result. Now, but remember, this is only p1 of x2. Now we have to take this and substitute this in here. So let's do that next. So sorry here, there's I just put these brackets in here, forgot those. Anyway, so now a2, as you see here, now we'll put this p1 of x2 that we've calculated, this whole p1 of x2 back in here. So then when we combine it, we end up with the following. So we'll have y2 minus y1 into, this will be y2, yeah, minus y1 minus y1 minus y0 into x2 minus x1 over x1 minus x0. Okay, we'll get that, and that'll all then be divided by, all of this is divided by what we had before, which is x2 minus x0 into x2 minus x1. Okay, we get that. Now if you see here, we can separate these out as well. What we'll do is the following. We'll group the y2 and the y2 and y1 together. So y2 minus y1 over x2 minus x0 into x2 minus x1. Okay, minus, we'll take these two, of course, and that'll give us y1 minus y0. Okay, and you'll see here the x2 minus x1 will cancel with the x2 minus x1, and it'll give us, in fact, x1 minus x0, which is left over, into x2 minus x0. Oh, sorry. Okay, so just to be sure, you see this x2 minus x1 here, this will cancel with this x2 minus x1 here. When I bring the whole thing under this whole thing, the x2 minus x1 will cancel with this, so it'll leave you y minus y0 on top alone, x1 minus x0 into x2 minus x0. That's what we have here. Okay. Now, a further grouping, we can clearly see there is an x2 minus x0 that's common here. This x2 minus x0 is common in both. So that leaves us with basically what we can do is actually say the following. And if you look at it now, a pattern has definitely emerged, and we end up with this. Okay, so this essentially, now if you look at it, this is there is a pattern now. This is y2 minus y1 over x2 minus x1 y1, sorry, wait. This is y1. So, and then we have y1 minus y0 over x1 minus x0, all divided by x2 minus x0. So now that's what we end up with. And so here's one thing I want you to note, if you will. If you see this term here and this term here, these look like the bare approximation of the derivative, in fact the secant line, the slope of the secant line, in fact, if you think about it, y2 minus y1 over x2 minus x1. So that would be approximating the derivative at y1, and this would be the approximation of the derivative, I'm sorry, y2, and this would be the approximation of the derivative at y1. So if you think about it, this whole thing, in fact, is the derivative is approximately the second derivative then, because you're taking the derivative at 2 points and then dividing that by the... This is kind of similar to, okay, and I'll put it in brackets, like something like the second derivative, okay, and the earlier one, a1, is kind of like the first derivative. That's something that you should, to recap. So what we're saying is that pk minus 1 is a polynomial that interpolates the points xi, yi, where I is from 0 to k minus 1. And what we are wanting to do with divided difference is find the pk polynomial that interpolates. Okay, so we want to find, in fact, pk that interpolates. Okay, so what we want is that this extra point xk, yk, and that should be added on to give us the pk interpolate. Okay, so this means, and the method we've been working at is pkx. This generates all, so in other words, if you start from P0 and then how do you get P1 and P2 and so on. So that would work out something like this. So it's pk minus 1 of x, of course, the previous polynomial, or k minus 1 points, plus some constant ak into x minus x0 into x minus x1 all the way up to the k minus 1 points. Okay, so you'll see here the matching, this k minus 1 and this k minus 1 here. So this, in fact, and then we use the fact that pk of xk is equal to yk, which is a given point. Of course, that's the extra point we have to find, okay, ak, right? And it turns out that ak, in fact, in this case, for instance, even, which we can quite clearly see, is yk minus pk minus 1 of x divided by, or xk here, sorry, pardon me, sorry, here, this is at xk, all right, divided by xk minus x0, xk minus x1, and all the way down to xk minus 1. So that would be the general formula, and of course, in this way, we can determine this. So this can help us to generate each one of these pKs, the next one from the previous one. Now, in altogether, of course, the divided differences leads to a one major polynomial, and that polynomial, in fact, for instance, the any polynomial of degree n would be defined as a0 plus a1 into x minus x0 plus a2 into x minus x0 into x minus x1, and it'll continue in the same way, plus all the way down here to a n into x minus x0 into x minus x1, and so on up to x minus x n minus 1. Okay, so that would be the form, the general form of the polynomial that would result. And what we've looked at are the various a's and how they're calculated, and this formula basically helps you to do that. So these a's, we've actually calculated them. In the next video, I'll show you how one can algorithmically try to do this with a very nice little tabulo, or a little table that actually helps us to calculate divided differences practically. So we'll stop here.